Today's topic is about the second part of organic chemistry. It's about alkenes. Alkene means between the carbon and the carbon, there will be a double bond, and we call that as alkene. But first thing, why there is a double bond or how this double bond is formed. So for this, you should understand the shells or the orbit. Like example, what happened as we have carbon. Carbon is 6 and 12. So when we write the electronic configuration of the carbon, it is 1s2, 2s2, and 2p2. This is the electronic configuration of the carbon. When we represent this in electron in a box model, so 1s is there, 2s is there, and 2p. And this 2p is divided into three categories, 2px. So basically this one is 1s, 2s, 2p. And this 2p is divided into 2px, 2py, and 2pz. Now what happened when we show the electrons? So 1s is having 2 electrons, 2s is having 2 electrons, and 2p is having 2 electrons only. But because the energy of 2s and 2p is comparable means like in the same order. So what happened? One of the electron which is present in the 2s will jump to 2p. So when this electron jumps to 2p, so there is 1s, 2s, and 2p, which is 2px, 2py, 2pz. So as one of the electron jump from 2s to 2p, so now the distribution of the electrons, the 1s will have 2 electron, one clockwise, one anti-clockwise. 2s will have 1 electron, 2p will have 1 electron, 2px will have 1 electron, 2py will have 1 electron, and 2pz will have 1 electron. So the electrons which are available for sharing is 2s, 2px, 2py, and 2pz. This is what happened for carbon. And this movement of electron from one shell to another, what we call this, we call that as hybridization. So that is hybridization. What is hybridization? Hybridization is actually the movement of electron from one shell to another. So now 4 shells are available, like 4 electrons are available. One electron belongs to s, one electron belongs to 2p, then 2px, 2py, and 2pz. That's why the carbon can form 4 bonds. So for carbon, the hybridization happened, that electron jumps from 2s orbital to 2p orbital, and we have electrons singly available which can form a bond. Now what happened? How it form a bond? Like it is forming a bond with, say, hydrogen. So for hydrogen, it is having only 1 electron, so electronic configuration of the hydrogen is only 1s. 1s1. So 1s1 means there is only 1 electron available. So for sharing, what happened, like for a covalent bond, actually it is formed by overlapping of the orbital. So hydrogen 1s is available, but for carbon 2s is available, 2px is available, 2py is available, and 2pz is available. So example, if we explain how a bond is formed in alkene such as ethene, like there's a double bond in ethene. So in terms of hybridization or overlapping of the orbital, how we can explain this? So as you know, the hybridization happened for carbon. So 2s is having 1 electron available for sharing, 2px is having 1 electron, 2py is having 1, and 2pz is having 1. And what are the shapes of these orbitals? As we discussed, uh, 2s will be spherical, 2px will be dumbbell in x-axis, 2py will also be dumbbell in y-axis, and 2pz also dumbbell in z-axis. So example, we want to show a bonding, the formation of a double bond in ethene. So ethene is what? Ethene is C2 and H4. So we have two carbon. So we draw two carbon atoms, and H4 means 4 hydrogen. For hydrogen, which orbital is available for forming a bond? 1s is available, 1s is spherical. So this will be the hydrogen orbital 1s. This is 1s, this one is 1s, this one is 1s. Spherical is there, that's why I'm drawing this. Now, for carbon, how many orbitals are available? 2s is available, 2px is available, 2py is available, and 2pz. So first what happened? One of the 2s, like this is a 2s orbital. So one of the orbital, the 2s orbital, overlap with one hydrogen. So when you can see the overlapping is there, when overlapping is a complete, this will be a covalent bond. And when overlapping is complete, what we call this bond? We call that as a sigma covalent bond. What is the meaning of a sigma covalent bond? A sigma covalent bond is formed by complete overlapping of the orbital. You can see this part, the orbitals are overlapping. That's why it is sigma covalent bond. Then what happened? The second orbital available for this carbon is 2px. So the first carbon used 2s and the second carbon also uses 2s. And that's also overlapping is complete. So first both form a sigma bond with one of the hydrogen. Then second they're using 2px. So if they're using 2px, so that 2px will overlap with the second hydrogen. So this is 2px. So you can see overlapping is, this one is 2s, overlap with 1s. Then this one is 2px, overlap with 2s of hydrogen. And same thing happen. This 2px overlap with 1s of hydrogen, and this was 2s overlap with 1s of hydrogen. So you can see there's a complete overlapping. So this second bond is also a sigma bond. Then the third orbital which is available, so 2s is used up, 2px is used up, the third is 2py. So when we represent 2py, the second orbital, I'll use another shade for this, say green shade. So it's representing 2py. So this is 2py overlap with 2py. So they overlap with each other because it's a complete overlapping. So 2py overlap with 2py. As there's a complete overlapping, so this is also a sigma bond. When there's a complete overlapping, the bond is sigma. This part also, because there's a complete overlapping, the bond was sigma. And this region as well, because there was a complete overlapping, so sigma bond was there. But now what we are left with? We are left with 2pz, the third orbital, the fourth one 2pz. So when we are left with 2pz, if I draw 2pz, like I'm using a black shade for this 2pz. So when I draw 2pz and the 2pz, so the 2pz cannot overlap with each other. Why they cannot overlap? Because look, it's a 3D If x-axis or y-axis is overlapping the z-axis, if this was x, this one is y, and this one is z. So if their y-axis overlap with each other or x-axis overlap with each other axis will not overlap. So this, the the z orbital like 2pz cannot overlap with 2pz. So as they cannot overlap with each other, but still they have attraction because electron in one moving clockwise, another one anti-clockwise. So this attraction is there. Attraction is known as the bond, but this is a weak bond which is known as the pi bond. So sigma bond is formed by complete overlapping. So when I represent the structure of ethene, carbon, between carbon and carbon there is a double bond, and between carbon and the hydrogen there is a single bond. So the distribution, because between carbon and hydrogen there is a complete overlapping, so this is a sigma bond. This is a symbol for sigma. So sigma bond is there, this one is sigma, this one is also sigma and sigma. And when double bond is there, in a double bond, one is sigma, it's not necessary up or down. One of them is sigma and another one is pi. So pi bonds are weak bonds, they can break easily because it is formed not by the overlapping of the orbital, it is only formed by attraction of the orbital when they are parallel to each other. But the other bonds are actually formed by overlapping of the orbital, which make it stronger. Is it clear? The formation of sigma and the pi bond in alkene. So whenever you have alkene, whenever there is a double bond, one of the bond is sigma and the other bond is pi. Sigma bond is by overlapping of the orbital, like the orbital overlap result in a formation of a sigma. But pi bond is not overlapping of the orbital, only their axes are parallel to each other and the attraction keep the electrons together. We call that as a pi bond. Is it clear? Any doubt? The formation of the bonds. Or should I repeat this? The hydrogen here, all of the hydrogen are 1s. This is 1s hydrogen. This is also 1s. This one is also, this 2s. This is also 1s. All of them are 1s. The hydrogen, all of the hydrogen are 1s. And for carbon, it is 2px, 2py, 2pz. So basically what happened, as you have carbon, as you can see the electronic configuration of the carbon, it is 1s2, 2s2, 2p6. So one of the electron jumps from 2s to 2p, which we call hybridization. Due to this hybridization, the orbital which are available for overlapping, the 2s is available for carbon, which is spherical, 2px is available, which is dumbbell, 2py is also available, dumbbell in y-axis, and 2pz is available, also dumbbell. And what about hydrogen? For hydrogen, it is 1s orbital available. So when we draw for ethene, like example, hydrogen is there, hydrogen. So if I say first for carbon 2s, so this is 2s of one carbon and this is 2s of the second carbon. So hydrogen overlap, this is representing hydrogen. So hydrogen overlap. Because this overlapping is a complete overlapping. So what kind of bond it is formed? This is a sigma bond. Due to overlapping, the reason why, even though both have the same shapes, but the size is different. Why? Because hydrogen it is 1s and for carbon it is 2s. Then I can draw, like example, I can even draw 2px. Say this is 2px for one and this one is 2px for the other one. So they also overlap with each other. So because the overlapping is complete, so this will be sigma bond. Then you can take 2py and you take 2py and you can this overlap with hydrogen. So this overlap with one of the hydrogen, because the overlapping is complete. So as the overlapping is complete, that's also a sigma bond. But what about 2pz? Like example, if I draw this is 2pz for one and this is 2pz for the other, you can see now they cannot overlap with each other. As they cannot overlap with each other, the orbital, they will have a pi bond. Attraction will be there, but this bond, because the orbital cannot overlap, so it will be a pi bond. So we have sigma bond and pi bonds. The double bond, whenever double bond is there, one of the bond will be sigma, and one is pi. And pi bonds are weaker as compared to sigma bond, because pi bonds are formed by attraction of the electron which are present in the orbital, but not due to overlapping of the orbital. Is it clear now? The formation of the bonds. In alkene. So basically, naming these alkenes, how we can name these alkenes. Alkenes are known as unsaturated hydrocarbon. Why we call them unsaturated? Because they have a double bond. And the general formula of alkene is CnH2n, means the number of the hydrogen is always twice as compared to number of the carbon. How to name these? If we have two carbon atoms in the structure, that's why the prefix will be eth. They have a double bond between them, that's ene, so it is ethene. If there's a three carbon atoms, then it will be prop, the prefix prop, and because there's a double bond, so it is ene, so propene. The position of the double bond is also important. So according to this position, like example, you can see a double bond is present between the first and the second carbon. So we call that as but, because there are four carbon atoms. One is the position and ene is due to the double bond. But when we number four carbon atoms, 1, 2, 3, 4. So second position we have a double bond. That's why it is but. 2 is the position of a double bond and ene. So but1 ene and but2 ene are the two isomers of each other, or structural isomers of each other. And how this formation occur? This will result in a formation of another type of isomer, which we call a geometrical isomer. Basically what happened, as you can see, the carbon maximum can form four bonds. But how this formation of the bond occur? Two of the bonds are in the same plane. One of them is into the plane. And one is out of the plane. And what is the bond angle? Because the carbon can form four bonds, four different bonds are there in a different dimension. So it will be a tetrahedral with a bond angle of 109.5 degrees. But this is what happened in alkanes. Alkane means when the carbon can form a single bond. But what happened in alkene? So as in alkene, the carbon form again 4 bonds, but 2 of them are double, like in the same direction. So the 2 bonds which are in the same direction, they're in the same plane axis. So one of them is in and another bond is out. So due to this double bond, there is a restriction in the geometry. Like what happened? One of the molecule can be in of the to the plane and another one is out of the plane. So this will result in a formation of another type of isomers, which we call geometrical isomer. So what happened in geometrical isomers? Like example, C double bonded with C. One of them is in. So one of the bond will be in and another one is out. So we can represent this in and out by a wedge and a dash line. So one is in, another one is out. Now, because of this, there is another isomer. What we call this isomer, we call that as geometrical isomer or stereoisomer. What happened in stereoisomer? If the heavy group means in terms of mass, if heavy groups are on the same side and lighter groups are on the same side, so what we call that? We call that as cis or Z. Means before the name we use the term cis or Z. But if heavy groups are the opposite side, like between the carbon there is a double bond, one of the bond is into the plane and the other one is out of the plane. This dashed line is not representing like number of bonds, it is representing the plane, like one is in, another one is out. So heavy groups are the opposite side, like one is in, another one is out, and lighter also one is in, another one is out. So what we call that as a trans or E. So this will result in a formation of cis and trans isomers. Basically, what are cis and trans isomers? Due to the double bond, there's a restriction in the geometry. Like the heavy groups have two possibilities: either they will be in the same plane or they may be in opposite plane. And due to this, it results in a formation of geometrical isomer and also known as a stereoisomer, cis or trans. Cis, it can be cis or Z or trans or E. Example, you have butene. So butene means when I draw the structure of butene, this will be CH3, CH, double bond CH and CH3. Now, if I draw this in terms of the plane, so how I'll represent the carbon-carbon double bond is there. Like these are the two carbon which have double bond. Now you can see hydrogen is there, like carbon-carbon double bond. This is a carbon-carbon double bond. Hydrogen is attached. Example, hydrogen I attach at the bottom. So if hydrogen is at the bottom, like in out of the plane, then CH3 will be into the plane. Same thing, the hydrogen is attached. Example, I attach out of the plane, so then the other CH3 is into the plane. When you check the heavy group means in terms of mass. So which one is heavy group? CH3 is heavy. So both CH3s, like when I compare these two, this carbon is there. When I compare which group is heavy, the group which is connected or attached into the plane is heavy. Same thing, the group which is attached into the plane is heavy. So both heavy groups are in the same side. So what we call, when heavy groups are on the same side, so we say it is butene, but we say it is cis butene. Or we can also say it is Z butene. So what is the meaning of a cis or a Z? It means they're on the same side. The heavy groups are on the same side. But what is the second possibility? If there is a double bond between the carbon atoms, so what is the second possibility? Like hydrogen may be attached into the plane and CH3 is out. But for second one, CH3 is into the plane and hydrogen is out. So you can see the heavy groups. Heavy group, you check the mass. So when you check CH3 is having more mass, here CH3 is. So heavy groups are attached. When I check the carbon, the heavy group is attached opposite side. So when heavy groups are attached to the opposite side, then it is trans butene, or we can also say it is E butene. Even like both of these CH3 are attached at the bottom and hydrogen is up, that will also remain cis. So idea is that the geometrical isomerism, why it arises? It arises due to the restriction of the geometry. Like we have only, if the carbon can form 4 bonds and out of the 4, 2 of them are in the same plane with the same another element on the same axis. So there is only restriction in the geometry that the other 2 which are attached to a carbon can be in or out. And due to this restriction in the geometry, it will give rise to another kind of isomerism known as geometrical isomerism. So when they are on the same side, the heavy groups, we use the term cis or Z. When they are on the opposite side, we use the term trans. Is it clear? The geometrical isomerism, or also known as, basically stereoisomerism, is of 2 types. One is known as geometrical isomerism, another one is optical. Geometrical isomerism you will study in AS, and optical you will study in A2. Is it clear? The geometrical isomers of butene. So basically, butene is having 2 geometrical isomer. One is cis butene, another one is trans butene. But if we try to draw, normally when the same groups are there, when the same groups, because heavy group can be different as well. normally when same groups are there, we use the term cis, same groups on the same side. When same groups but in opposite side, we normally use the term trans. Like if I draw another isomer, if I draw butene, so in case of butene, butene is CH2, double bond with CH, CH2, CH3. So when I try to draw the geometrical isomer of this, the two carbon have double bond. So these are the two carbon which have double bond, two hydrogen, one in, one out. For this one hydrogen is there and then CH2 and CH3 is attached. So you can see when I check the heavy group, for a right hand side carbon, this is a heavy. But for left hand side carbon, there is no heavy group. I cannot compare. So when we cannot compare, both atoms have the same mass. So what we call, we say it does not have any geometrical isomer. So but1ene or butene does not have geometrical isomer. Because for this carbon, we cannot compare which one is heavy. Both of them are hydrogen, so we cannot compare. Is it clear? So this is a part which already I discussed with you. You can see this is a carbon. Carbon maximum can form 4 bonds. So 1, 2, 3. And the fourth one, like when the axes are only parallel to each other, but they cannot overlap. So there will be attraction from the top and the bottom. And this is called 1 pi bond. This is not like 2 pi bonds, but still it will be a weaker because the overlapping is not happening here. So carbon-carbon double bond consists of one sigma bond and one pi bond. And the pi bond are exposed and have high electron density, and therefore they are vulnerable to attack the species like electrons. And these species are known as electrophile. Electrophile means, that's the last class we discussed. Electrophile means the species which is attracted towards electron rich side. So due to the pi bond, the species are attracted, or these are known as electrophiles. And you can see the formation of the pi bond. So hybridization is also of different types. sp3 hybridization is there, sp2 hybridization is there, and sp hybridization, but you don't have to go in detail for that. So you can see between the carbon and the carbon, there's a overlapping. So when there's a overlapping, the bond will be sigma. But the axes are parallel, but orbital cannot overlap. So which kind of bond this will result? This will be a pi bond. So first thing, this is a formation of a sigma, and then what is the formation of the pi? You can see attraction is there. So pi bond is formed by a sideway overlapping of the two orbitals above and below the molecule, and pi bond is a weaker than a sigma. Then what is stereoisomerism? Stereoisomerism, like what we have, stereoisomers have the same structural formula, but they have different spatial arrangement like geometry. And this stereoisomerism is divided into two classes. One is called geometrical, another one is optical. But you will learn geometrical isomerism. What is geometrical isomerism? Due to a carbon-carbon double bond, there is a restricted rotation for around. Restricted rotation means, like, because there is a carbon-carbon double bond, so only two possibilities are available, that either it can be in or out. So only two possibilities. Like if I say two molecules or two groups are attached, H and L. H means heavy, L means lighter. So what are possibilities? H can be up, L can be down, or the second possibility, L can be up or H can be down. So this is a restricted rotation around a carbon-carbon double bond, and there are two groups or atoms attached to both ends, which result in a formation of result in a cis or Z or trans or E. Like you can see here, the carbon-carbon double bond is there. The heavy group is at the bottom. You can all, if you find it difficult to represent in terms of wedge and the dash lines, you can also use, if you find this difficult, you can also use a special uh, arrangement in which you just represent, like one is at the top, another one is at the bottom. But actually what they mean, like one of them is into the plane, another one is out. So heavy groups are on the same side. That is why it is cis or Z. Heavy groups are on the opposite side. So it is trans or E, the priority group. But for but1ene, there is no priority group because both have are hydrogen are there having the same mass. Is it clear this point? The geometrical isomerism.